At first, I would like to present the motivation of my work, why we're studying actually the titanium dioxide nanoparticle. For those who is not familiar, for the titanium dioxide nanoparticle, they have very incredible abilities like high surface area, and they are actually low cost in production. They have a lot of stabilities, mechanical stability, chemical stability, high refractive indexes, and resistances, so which make them very important in several applications, like you see in the right image here, for cosmetics, energy, and medicals like drug delivery. And one of the most important application for them is the photocatalytic application. But as there anything it's not perfect, there is also advantages for the titanium dioxide nanoparticles, since they are exposed to us in direct and indirect way. And as the research proved that the consequences of their exposure causing cancer risks. Therefore, our motivation to work to control their aggregation and to understand how they are interact with the environment. But for doing so, we have to understand, since my project is actually focusing on their behavior in the natural water, we monitoring for important parameters that affecting directly on their behavior, which is pH, the ionic conductivity that they are exposed to, the temperature of the water, and also the alkalinity carbonate content. So how we design our experiment, we design our experiment by placing this particle inside the river water at certain exposure time. But the average that we are working on right now is roughly 2 days. We're doing this by choosing a certain dialysis bag with certain molecular cutoff, molecular weight. After that, after they get cleaned and purified and everything, we have a modified nanoparticle with the biomolecules and protein that we want them to get attached to our surface. After that, we're scanning them with scanning force microscopy to investigate how this adhesion behavior works. For our first samples, we choose the spot of Quench River in Landau, and our first sample was chosen to be from 700 nanometer to 2 micrometers. We're going to further smaller sizes in the coming months, but we choose these sizes at first. And like you see, as I've explained in the second slide or third slide, that the characteristic of the water have been monitored at the first regarding the 4 important parameters that we're looking for reproducibility. So we can see how the adhesion behavior affecting during the change of these parameters. This is all this is about. So of course, all of you are familiar with the fluid AFMs. It's modification for the normal force microscopy, which allow us to control the fluid on the surface with using a special microchannel cantilever. And for my work I'm focusing using two important parts: the nanopipette with average aperture opening of 300 nanometer, and the tipless fluid AFM with 2 micrometers. Then after applying native pressure, I can capture these particles to investigate their behavior, like I'm going to explain to you in the next few slides. We choose the glass substrate for working not just because it's transparent and it is not affecting our interpreting of the data. Since we're looking at the samples under the microscope, we need a transparent surfaces. We use also them because they have low roughness abilities in their topography, which is not going to interrupt our data like it's appeared to you here in the height image and the error signal images. After that, I would like to show you some results for the force microscopy after capturing these nanoparticles from the surface. But before that, I have to see how the behavior of the cantilever is working before capturing the particles. At first, we're applying holding negative pressure under pressure in the range of 200 millibar to negative 220 millibar, and the behavior of the force curves as they are recording while I'm trying to approach the particles is starting to save some adhesion values in the picometer ranges. After that, when you start to feel the particle from the surface, it's start to do some hesitation in the retrace curve, which give an indication that the particle is approaching the opening aperture due to, of course, the attraction force that have been created under the negative pressure. So after they got picked up, here the sketch is representing after the pickup of the particles, the adhesion forces regarding the parameters that I have showed to you at the first few slides. They give us an adhesion value in the range between 5.8 nanometer to 11.7 nanometer. Of course, there is a lot of variation in the force curve in the middle, but for saving time for this presentation, I just give you the minimum value and the maximum value that I have got so far for these results. So as I explained, since the parameter is so important, we're focusing on changing all the parameters together to maximize opportunities to investigate how this changing in parameters can cause difference in the results. To zoom out these results, this table, this have been done by our partner in Landau University, investigating several spots in Germany. And as you can see, this was the first experiment that have been done, and next experiment ongoing experiment, we still investigating how the effect of higher alkalinity and higher electronegativity on the adhesion behavior of these particles. This is actually very important because it's affecting the characteristics of the adhesion behavior, and therefore is going to, of course, going to change the force curves, and the results is which for the attached nanoparticles. And since these results are a little bit difficult to interpret, there is a models experiment that we are following to compare our work with. The first model experiment that this particle, we will have too many attached particles at the first, but this for later, for simplicity, we're going to investigate them by using the IR spectroscopy with a single species on the cantilever. There is a model experiment here explaining a comparison point where the cantilever is get modified with the single particles, and we're trying to do this, but not with the cantilever itself, with the modified titanium dioxide nanoparticles.
We have 3 minutes left.
Okay. For wrapping up, what I'm trying to tell you that this particle is going to be just modified later on with one single biomolecule or proteins, and then getting approached to the surface to see how the force curve is going to be differ from all the particles that attach to the titanium dioxide surface to just one molecular particle. So we're taking the big image and then going to the smaller image for later. Other model experiment that we look up to for our experiment, that those results have been done in our group for 3 different proteins: fibronectin, PSA, and lysozyme. And as you see here, the effect of the pH is quite significant on the respective adhesion force that we got as a result of that. Besides, there is a more important factor that we are also investigating, that the contact time of approaching of these attached proteins from the nanoparticles into the surface, since of course with passing of the time, this means the rupture of the molecules of the proteins, and of course this is going to change the result significantly. And to wrap up what's most important for this project, that we're investigating the main points about how the effect of the protein is going to affect the change of protein, is going to affect our adhesion force, how the contact time is going to change our force curves, and the presence of pH and the ionic strength. To conclude what I have been said for the last roughly 9 minutes, the titanium dioxide nanoparticle exhibit different coverage when they are exposed to the environment. We are going to investigate this attachment by using the force curves, by using the fluid AFM. We need model experiments to look up to and to compare our work with, and like I showed you in the last few slides. And the most important points that to show how these single proteins later on is going to be differ with the contact time, the presence of pH, and several other environmental parameters that could be, of course, available in the river water. Before I end up my presentation, I'd like to thank my group in Technische Physik Kaiserslautern, our partner group in Landau, and all the funding institutes. And thank you all for your kind listening.